welcome to my show. Hopefully I've got audio. Yes, I have. I know many people don't watch me live, but I don't really mind because it's a bit of fun to get in here and have a bit of look at things. Today, I'd really like to look into radars because there's something about them that I think a lot of people completely misunderstand. And there's some principles that are really important if you want to understand radar operations. I'm not going to go too deep. It's going to be quite high level. The intention is to give you a bit of an introduction to how radars used to work, and the principles of what I'm talking about still apply today. Let's get started having a look at the whiteboard and working our way through that one. And now we've done the wipe, here we go. Basic block diagram for one of these things looks like this. They consist of a series of components and they basically hook them together. And this is only a block diagram. The block diagram is for a good reason. If I gave you more detail than this, it would be way too complicated. But the principle of operation, anyone that's worked around this stuff will tell you that they're not that difficult. All this thing duplex does is it enables you to connect the signal from the antenna to either the amplifier or the transmitter. I have seen these things up close and personal because I've worked with this kind of equipment. They're very, very simple. All they do is they simply cut the path to the amplifier off when the transmitter's going. That's it. That's all they do. They're completely autonomous. There's no electronics in them. They just work. They work very well. For the transmitter and pulse modulator, it's very, very simple. All we do is we generate a pulse, pass it on the transmitter, which takes the pulse and turns that into an RF signal at a certain frequency, and out it goes. That's it. Very, very simple. Just excuse me a sec. I have a visitor. Won't be very long. All good. Back to what I was talking about. So basics of the radar is simply to get the whole radar picture out there. And the basics were generate the pulse, give that to a transmitter, which gives you the radio signal, and out it goes. Nothing really complex about it. Some things are really important. If you've never seen this before, they do not put a perfect square wave into these. Perfect square wave is too ringy, right? These edges here basically are quite messy. What they do is they pulse form. This is a little bit rough because it's being done by hand, but it's called a Gaussian pulse. What they do is they have a rise in a distinct fall time, and they have a peak power in the middle. The whole idea of that is to make sure that you don't produce rings, which actually give you multiple frequency output. So that's just there for that purpose, and that is controlled by something called the pulse forming network. Very straightforward. That goes to transmitter, and it goes in the peak pulse power. Depending on what your application is, it's not unusual for some of the long distance radars to be talking about 1 megawatt power inside the pulses. Very, very simple. Now, things I want to look at include what makes radars actually get interference. It's going to clean up my board a little bit because it just needs a tidy up. The things that they have had problems with in the past is if two radars are placed too close to each other. So here's radar number 1, here's radar number 2. And when they start looking at the signals, I know these look like a sunflower at the moment. Basic idea is that this radar signal gets into that radar. It produces interference. So on the scope, these guys just see dots as a result of that radar's outputs. And these guys see exactly the same thing. So it wasn't so bad when they built the first radars, it wasn't a problem. But as they went along, added more radars, they got closer and closer together, this started becoming a problem. So how did they resolve it? You had to find some way of differentiating between radar A and radar B. Without that differentiation, you simply can't make the radars work. So there are a couple of techniques. one of the techniques is to take the RF pulses and put two of them together. And the timing between this one and this one was used to help you detect radar from radar. Now that was a pretty straightforward way of doing it, because radar B simply had a different timing, and the circuitry down through here where you did all your detector work, you actually looked for that differential. Then it got more complicated. More radars got introduced in close proximity to each other. The radars on the aircraft, radars on ships, radars on the shore. It really gets messy. So this wasn't a viable way to do this anymore. What they then started to do with respect to the time signals is the pulse pairs were moved around slightly. You see a pulse pair here, and you get a response back. And then you get a pulse pair which have moved in time, and you get a pulse back. Now, that makes the work of the detector a lot harder. The detector now has to be able to work out which pulse pair and which signal in return match up. It's a timing thing. If these pulse pairs go out and come back, and this represents, let's just say it's 10 nautical miles, just using nautical miles because that's the thing I was most familiar with, 12.4 microseconds, 124 per radar mile. That's going to take 120 microseconds to come back. Quite simple. If you move the pulses, then the timing from this pulse to this pulse is now about the same. So you can pretty reliably say, yeah, that's going to be the same one. The technique for doing this is given the name jittering. One of the black one. It's very, very simple. They simply built an oscillator that was unstable, deliberately introduced jitter, make the item run its own directions. Now, guys, I'm not looking at any beads, so I don't know if anyone's looking, but I may have a very quick look just to see what's going on. If there's anyone here chatting to me, I haven't seen your name. Yeah, I'm going to know about that. G'day, Peter. I've just had an apple handed to me. Thanks, mate. In any case, that was it. So they introduced jitter. Now, some of the more complex systems, they have gone substantially further than just introducing a bit of jitter. I didn't want to below there again. I do like whiteboards. They're quite handy for just roughing out a quick diagram. The intention is just to give you really simplistic overview of all this stuff. Everything I'm talking about is easily researchable. Anyone that wants to research this would find the exact same information I'm talking about right now. Now, some of the more complex ones, and this is where I've got to be a little bit neater with my diagrams. They actually took the radar pulses and they passed them through a special circuit on the transmit side, and they would say half one, and then they would invert the sine wave. Really interesting stuff. This is a form of encoding. So now you had a sine wave, which was actually being modified as part of the transmit sequence. So one cycle, two cycles, then the third cycle is the opposite way. Then the next cycle begins as normal. It doesn't, it actually starts going down and up. Two cycles, and they repeat that pattern for as long as the transmission is going into place. So this now required the detector to be capable of detecting this, as well as the stuff I mentioned before, which is the jitter pattern. This gave you a bit more sophistication and enabled more radars to be packed closer together. And these are really basic things that had to be solved in the 1940s. Most of the technology in this would have been valve-based, pretty much guaranteed. Very little of it would have been based on transistors and hybrid with valve. More often than not, your transmitter will be one or two devices. One of them is called a klystron, and the other one is called the magnetron. Correction. So the magnetron was preferred because it produced the best power out. Very, very simple device internally. Klystrons were actually a big valve, but magnetrons, while they had a vacuum in them, worked very differently and were very extremely reliable. So these ones were basically a glass tube valve, and they worked like that. And then when you introduced this kind of encoding, you had to actually put it in your transmitter line. So these things had to handle the power as well. So let's have a little talk about the power that does come out of the transmitters, because I think that's a pretty important thing as well. It's not immediately obvious how you would work out what the power coming out of a radar system looks like. Let's just go back to our pulse pairs. Nice Gaussian pulses. Please not say they look like something else. I'll get most upset. No, I'm kidding. Within these pulse powers, you measure the pulses by looking at certain characteristics at the 50% mark, about halfway up the total height. That's where we do the pulse width. So there to there would be classed as your pulse width. The pulse repetition frequency is simply at the 50% point. So you look at, let me change colors so it's a bit more obvious. Pulse repetition frequency is here to here. Now, technically, what I've just shown you is called the pulse repetition time. And pulse repetition time happens to equal 1 over pulse repetition frequency. So if these pulses were coming out often enough, then you would find this would be a lot of radars. You can hear it on your radios you drive underneath them. They generally output the pulse pairs at about a 1 kilohertz rate. So to complete this diagram, we now need to go to the extra bit where we've got the next pulse pair. Yeah, I know I'm a terrible drawer. These look more like cacti. Basically, so what you pulse with, all the characteristics. The other characteristic, which I haven't talked about, is going to be the leading edge of these things, because at 10% to 90% is how you measure this. They actually look at 10 to 90% is called your rise time. So it's RT, rise time. And the rise time gives you other characteristics, but basically when we look at this, we have a very rough and quick way of working it out, because the pulse widths generally around about 1 microsecond, up to probably 5 microseconds. I'm not sort of familiar with anything that goes outside these sort of characteristics, but basically you transmit your power for 1 microsecond or 1 millisecond, depending on what you want to do. The pulse pairs, working in pairs, you actually have to look at, there's a certain amount of power in this one and a certain amount of power in this one. And when you amortize that over, and I didn't give you the right information here, PRT isn't where I've marked it. It's actually start of this one through to start of that one. That is your pulse repetition time. So let me go back here again to get your power output. It's amortized over time. So if you take into account pulse times, there's about 2 microseconds of time you are transmitting power. Divide that by the pulse repetition time for 1 kilohertz is going to be 1 millisecond. And we generally find 1 megawatt in those bigger radars. When you do the calculation, that's 2 over 1,000 multiplied by 1.6. So that becomes 2 minus 3. Take that off there, and 6 minus 3. What we actually see is overall we use about 10 to 3 watts, about 2 kilowatts is being drawn all the time for the radar. There was a radar that Michael Toon talked about and said it was around about 500 kilowatts, so it's about half this power. So it drew constantly from the power source about 1 kilowatt, and it would put the pulse power into the big pulse as it came out. Okay, so that's basics of radar. I'm not going too in depth for a reason that's just it is really technical. The schematic diagrams can be very confusing if you're not used to this type of electronics. Okay, I'm sure there'll be questions, and I'd just like to thank everyone for a few minutes of their time today and having a look at this with me. I certainly enjoy sharing the knowledge of all these things, and working with them has been a lot of fun as well. If you have any comments, please put them in the chat. I will have a look at that in a minute. So back to where I'm going. So now we've talked a bit about radars. We've been through what they look like in terms of the block diagram. We explained some of the phenomena that they actually had to deal with over a period of time. So there were pulses, then they double pulses, and they jetted the pulses with an unstable oscillator deliberately designed to randomize its location. The detector circuit in there now has to do more work to actually detect properly. Modern radars, which use Doppler, still output pulses, but they look for a different thing. The detector has to detect a completely different response to these things. Okay, guys, thank you very much for watching and listening. It's always a pleasure. Don't work too hard. It's a lovely weekend. I hope you all have a really good night. It's nearly time for me to say enjoy your night.